In this video I would like to talk about Vlans, and I'm pretty sure you came across that term more than once, and maybe you wonder, what is that Vlan exactly? How those Vlans even work? I mean, what is the technology behind them, yes? And what is, for example, dot1q tag, or what is default Vlan? And that's all what we are going to talk about today. So Vlan stands for Virtual Local Area Network. And for now, we can skip maybe that word virtual. We will focus on the second part, which is Local Area Network. What is that Local Area Network exactly? A local area network is something we already have in our homes. It's a collection of our devices that are connected to our router, either wired or wirelessly. So our phone, our laptop, smart TV, wireless printer, if they are all connected to the same device that our service provider gave us, and if we didn't change any configuration on that device, then all our devices at home create what is known a local area network. And if we configure our devices to be visible on that local network, then all those devices in our home can see each other and they can communicate with each other. And that is LAN, Local Area Network. So what is VLAN then? Let's say we bought some CCTV cameras, and we don't want those cameras to be in the same local area network as our computers or our home servers. I mean, I need those cameras, but believe me, it's better not to have them in the same network as all of our other devices. God knows what type of software is on them and what it does, if it spies on us or worse, I don't know. What I can do then? The fact is, I can split my single local area network into multiple isolated virtual local area networks. In computer networking, you will often hear that term, virtual. For example, when you split one big server into smaller logical servers, you call them virtual servers or virtual machines. It's the same with LAN. Once you start dividing your LAN into smaller chunks, you call those chunks virtual LANs, which simply means they will become logically or virtually separated from each other. But anyways, I was talking about those CCTV cameras. But you might also want to separate other network devices. You want to separate your network even further. Maybe you want to keep your printers in separate designated VLAN. And maybe you want to separate servers from the PCs, etc. This is basically the way that every single company separates their network as well. It's safer, it's easier to manage, and you also, what you do is you make smaller broadcast domains. But let's not talk about broadcast domains maybe. Let me simply show you how it's done and how VLANs can make all those different devices completely separated from each other. And for that I will use a free software called Packet Tracer. It lets you simulate real-life computer networks. And you can get this tool for free. This Packet Tracer is free, you just have to sign up to Net Academy website. And it's not sponsored video, it's simply a really nice tool, and it's free, so can't complain. And as you can see, I created a very simple network with just 4 computers, and they are connected to that single switch in the middle. And currently they are all in the same LAN. I didn't do anything. The only thing I did here is I configured IP addresses and MAC addresses for all those devices. But we will split that network later on, so you can think of those top devices as maybe computers and the bottom devices as maybe those CCTV cameras that we want to isolate. At this stage it does not matter, because as I said, at this stage they can all talk to each other because they are in the same LAN. But you might say now, Marek, but I don't have a switch at home. It doesn't really look like my home network. Well, the fact is, you already have a switch. That device you got from your internet service provider, and although we call it, we usually refer to that device as a router, it's really an all-in-one device that in fact has a switch built in. And all devices at home that connect wirelessly or are wired to those usually yellow ports, they are connected to that built-in switch in that all-in-one device. But alright, back to our example. We have those 4 computers, and since all those computers are on the same network, they can connect and they can ping each other. And what I mean ping, I can, for example, if I click on that device and I go to command prompt, I should be able to ping, let's say, PC1, which has IP address of 10.0.0.1. And you can see it works fine. We have the response from PC1, from the IP address 10.0.0.1. As I said, each computer currently has assigned IP address. I assigned it manually, and that IP address is known as layer 3 address, plus it also has MAC address, which is also known as physical address or layer 2 address. And if you want to learn more about those addresses, and about those layers, then please watch one of the previous videos when we talked about OSI model. But for now, let me just tell you that this switch in the middle does not have any idea what an IP address is. The switch cannot interpret any layer 3 information, like this IP address. This switch is a very simple device. It's really just a connection box that has very limited information. And the fact, the only information it holds is what MAC address is connected to each of these ports. MAC address is something you can check on your computer if you run IP config/all. You can see this is physical address, which is that MAC address. This is something you usually don't configure. This is assigned by the manufacturer of the network interface card. But you can also see IP address, which you can either configure yourself, as I did here, or you will get this IP address automatically from your all-in-one device that you got from your ISP provider. And each device has different IP address, and it will have different physical address, layer 2 address, MAC address. You can see I simplified a little bit. I said DDD, but MAC address is a little bit longer, but just wanted to keep it shorter. I didn't want to type all those letters. Never mind. What I'm really interested in is I can close that. I can actually, this is called managed switch. So if I click on that, and if I go to CLI, command line interface, I can run command show MAC address table. And what I can see here, let me move it slightly. As I said, this is all this switch can actually see. It can see that MAC address AAAA is connected to port FA01 and MAC address DDDD is connected to port FA04. But why only those two are displayed anyways? Well, the fact is, the switch only knows about MAC addresses once it can see some traffic in the network. We did that ping, yes, from PC4 to PC1, so switch learned about those two MAC addresses. But it hasn't seen any traffic yet between PC2 and PC3. So it learns those MAC addresses and those ports only after receiving and sending some traffic. Which means, if I go to PC2, for example, to command prompt, and I ping 10.0.0.3, now we get the response from PC3. I can close it. If I open the switch configuration again, and if I run exactly the same command, show MAC address table, oh, interesting, it already forgot the previous MAC addresses. Yes, but if we run again, sorry, one sec, I will explain. I will say ping, we are on PC1, so 10.0.0.4, that's fine. And if we go to switch again, if I run that command again, now it can see all 4 devices. And why here it only displayed those two and not previous ones? Because it already forgot about previous MAC addresses. It keeps that information only for a while. It can also be configured how long it keeps that information in cache. But if it can't see any traffic for a while, it will simply drop that information. So how is that obtained exactly? Let's just step back and think what happens when I send ping from PC1 to PC4. The process is that PC1 creates so-called packet first, and that packet has several fields. One of those fields is called a payload, and in our example it's just a simple ping command. Payload is the data that it holds, this packet holds, and in our case it's a simple ping command. So that PC1 adds then another information to that payload. It adds so-called IP header, and that IP header will include the source and destination IP addresses. So source being a PC1 IP address, 10.0.0.1, and PC4 is our destination, so we'll put the destination address 10.0.0.4. However, that PC1 will also see that to reach PC4, it will have to pass through that switch in the middle. This PC1 is connected to switch using Ethernet cable, so it knows it has to create another header. This time it's called Ethernet header. Not internet, but Ethernet, okay? This header will include source and destination MAC addresses. Because remember, this switch in the middle has no idea what an IP address is. So far, all the information that was created by PC1 is useless for switch, because switch can only read MAC addresses really. So PC1 simply adds source and destination MAC address as well. So in this case it adds AAA as a source and DDD as destination MAC address. And only then the ping is sent, and the first time this switch in the middle sees that incoming packet, together with Ethernet information, it's called frame. Packet is just with the IP information. It's like, it doesn't really matter. Basically, this ping is sent, the switch in the middle can see it, and it can see that the source MAC address is AAA, so it will save it in the MAC address table. However, at this stage, it doesn't know yet where is the destination MAC address, DDD. So what it does, it will send that frame out of all of its interfaces except of the interface that it received this frame from. And this behavior is known as unknown unicast. So simply it forwards this information further to all devices, hoping that one of them has that MAC address DDD and it will respond to that message. And the PC4 indeed responds to that ping. And once the switch in the middle sees that response from PC4, from now on it will know that PC4 is connected to interface FA04 and it will save this MAC address in its MAC address table. So this switch in the middle operates only using those layer 2 addresses, the MAC addresses, and only maintains that thing called MAC address table, where it records which computer simply connects to which port. But you keep looking at that and you're like, Marek, you're missing one important information. What is that VLAN? We've got VLAN information, yes? What's that VLAN 1? The thing is, we haven't configured any VLANs yet, and this managed switch by default will have something called default VLAN. If it's not configured with anything, all those interfaces and all those devices will land in the same VLAN called default VLAN. So basically, if you don't configure anything, you land in VLAN 1 in default VLAN. But now, I want to start splitting this network, this one local area network, into multiple virtual local area networks. How do I do that? Now we will see clearly why it's called virtual. The thing is, we are not changing physically anything. We don't pull any cables, we don't buy another switch. Physically it stays exactly the same, our network. We will only change the logical setup. And I will only have to reconfigure the switch. So the devices, like computers or maybe CCTV cameras, they will not even be aware that they land in some VLANs. This information is only configured on the switch in the middle. How do I do that? On the Cisco switch, I run command enable or simply en. I know these letters are very small, I don't know if I can even make it larger, but hope it's okay. So it's enable and it's configure terminal, which can be shortened to conft. And then, let's say we want these top devices, which are maybe our computers, we want them to be in VLAN 10 and the bottom devices will be maybe in VLAN 20, let's say. So what I can do, I can simply run command interface FA01. This is the interface I want to configure. I have to make sure that that interface is configured as mode access. So I say switch port mode access, not switch port, but switch port. Switch port access VLAN 10. We can see it says access VLAN does not exist, creating VLAN 10. The first port you want to assign to VLAN 10, if that VLAN is not pre-configured, then it will be created for you automatically, so you don't have to worry about it. But we want to put port FA2 as well in the same VLAN, yes? So I simply say interface FA02, and again, switch port mode access, I can use up arrow, and again, VLAN 10, switch port access VLAN 10. So let's continue, and we will configure PC3 and PC4 in VLAN 20. But remember, we don't touch the PCs, okay? All configuration is done on switch only. So I say interface FA03, switch port mode access, but this time switch port access VLAN 20. And VLAN 20 also didn't exist, so it will be created for me automatically. And the same for interface FA04, using up arrow because I'm lazy, mode access, VLAN 20. That's all. You will see that orange dots while it's being reconfigured on the switch, but you can see PC is not aware that anything changed at all. But let's now close this. Let's go to PC1 and let's ping maybe PC4. We did it, yes? just like what, minute ago or a few minutes ago. So let me just use up arrow and I will rerun the same command. Press enter. What happens now? Let's have a look. Something is different already, you can see it. And it says request timed out. But what the heck? I was able to access it, yes, just a minute ago. So what happened? What is different now? The fact is, if I go back to switch and if I run show MAC address table now, sorry, I have to exit first, we can see just one MAC address. Isn't that interesting? Well, the thing is, if you look carefully, if you look again, you will also see VLAN number has changed. The thing is now, top PCs are in VLAN 10 and the bottom PCs are in VLAN 20. And we tried to ping PC4 from PC1. What happened this time, that ping was also sent to the switch, but this time switch will only forward that information to the interfaces that are in the same VLAN. And PC4 is no longer in the same VLAN. So switch checks that frame, it can see it's supposed to go to MAC address DDD, but it doesn't have MAC address DDD in VLAN 10. Switch will only check MAC address table for VLAN 10. And because this MAC address is not there, it will simply send it out all of the ports, but only those ports that are in VLAN 10. And the fact is, none of those PCs have MAC address DDD, and none of these PCs have IP address 10.0.0.4. That's why we simply don't get any response. The PC will say request timeout, and the MAC address will only stay with that one source MAC address. But what we can do, we can go to PC1 and PC3, maybe PC1 first. We should be able to ping 0002, because it's in the same VLAN. It works, as you can see, it works. I can now go to PC3 and I should be able to ping 10.0.0.4 because they are also in the same VLAN, VLAN 20. And now if I go to switch again, if I run show MAC address table, now we have full picture. This ping worked from PC1 to PC2, and ping from PC3 to PC4 also worked, so switch was able to learn all those MAC addresses, but they are in completely separate VLANs now. So they are not able to talk between VLAN 10 and VLAN 20 are completely separate switches. You can consider them as being completely separate devices. And in fact, our switch is currently split into 3 little switches, because whatever you connect to port FA01 and 02 will land in VLAN 10, whatever you connect to FA03 and 04 will land in VLAN 20, and all the other ports, it has 24 ports. If I hover over it, should display them all. Look at that. All remaining ports, if I connect something there, they will land in default VLAN 1. And what really happens in the background here is that the PC still sends the same frame out with the ping information, with the IP information, and with the Ethernet headers. However, once switch receives that, it will add yet another information. For any traffic that lands on port FA01, it will add something called dot1q tag or VLAN tag, and this dot1q tag will have the information that this traffic belongs to VLAN 10, and within that switch it will only be forwarded further based on that information. And then when it's sent out towards PC2, then this information will be stripped off. The VLAN information is only inside that switch. The same for PC3. When switch receives that ping, it will add the information that this traffic belongs to VLAN 20 and will only be forwarded to devices that are connected to the interfaces that have the same VLAN tag. But once that ping is sent out towards PC4, this VLAN information is also stripped off. PC is unaware that it belongs to any VLAN. It all happens within that switch. And if we had another computer that connects to that switch on default VLAN, on VLAN 1, then that dot1q tag is not added. But if we had only one computer connected to one port on VLAN 1, it wouldn't be able to talk to anybody, because devices connected to default VLAN can only talk to other devices connected to the same default VLAN, which by default on switch is a VLAN 1. But VLAN 1 simply means, or default VLAN, simply means no dot1q tag is added. And it works this way, so you can connect to some old or cheaper devices usually unmanaged switches, where you can't configure VLANs. Very often at home you will have unmanaged switch. You can't even log on to that switch. You can't run like any of those commands. You haven't got any view what's going on inside. Those switches will only have default VLAN, VLAN 1, and you can't reconfigure them. So basically this is the method where you can connect to, this is managed switch, and you can connect to it unmanaged switch, but they will only be able to work on that default VLAN. I hope that makes sense. And if you wonder whether there is a maximum number of those small virtual networks, those VLANs, that can be created on that large switch, then the answer is you can create over 4,000 VLANs. So many more than you will ever need. But yes, there is a maximum amount of VLANs that you can create on a single switch. Remember that if you want to learn more about computer networking or Linux administration or AWS Cloud Python programming, you can join Automation Avenue platform, where you can find hours and hours of very useful materials. That's all I wanted to say today, so I hope that makes sense, and thank you for watching.